So good afternoon to everybody. For me, it's a good pleasure to have you all here in this Colloquium Plus institutional celebration for the 14th anniversary of CRM. Say that it took 40 years to arrive to the maturity, and now we have to think what we want to be when we grow older. We will start with the CRM Colloquium. This will be the second colloquium in the new CRM series of colloquiums. As I explained the other time, it was more or less 1 year ago, we try to organize, as usual, as a service to the community, high-quality colloquiums, and in this case, high quality means colloquiums that can be motivating for young students, even for researchers, for senior researchers that want to do new things. And so we are devoting a lot of efforts in those colloquiums. And this time, we took the opportunity to make it was in part a coincidence, in part it was in purpose, to put together the colloquium with the institutional celebration that it will take place at 6 o'clock. So we are enforcing this celebration because, as it should be in the scientific world, we'll have a scientific part and also an institutional part, which is the best thing that we can do, in my opinion. I will not talk anymore. My role is to explain that this is very important from the institutional point of view, this colloquium, for the CRM and for the people here, for all the people here. And I will give the word to Alberta Zarias, who will act as a chairman of this colloquium and will introduce the speaker. I had the absolute privilege of having lunch with Madhu, and I enjoyed very much the conversation, the scientific conversation we had. I'm sure that this colloquium will be highly motivating and it will be interesting for everybody, and I'm sure that we will enjoy it very much. So thank you for being here, Madhu, and thank you for being here, everybody.
Thank you very much, Luis. Madhu Sudan is a Gordon McKay professor at Harvard University since 2015. Before that, he was principal researcher at Microsoft Research and professor at MIT and research staff member at IBM Research after he graduated from Berkeley in 1992. So his PhD thesis in 1992 from UC Berkeley was the recipient of the prestigious ACM doctoral dissertation award, and this was the first award of a series of very prestigious awards that Madhu has received. In 2002, he received the Nevalina Prize that is awarded by the International Mathematical Union for outstanding contributions to mathematical theory of computation and information science. Madhu is also a fellow of the ACM, of the IEEE, of the AMS, and is a member of the American Academy of Sciences of America. So Madhu's contributions to theoretical computer science are uncountable. His award-winning thesis included full proof of the so-called PCP theorem, probabilistically checkable proofs, which is still today considered one of the deepest results of the theory of computing. To give you an idea, one way to think of the theorem is as a sort of a unification theorem that unified two strands of complexity theory that were being developed in parallel at the time. So there is the NP-completeness theory that Steve Cook started in the 1970s, and there was the theory of approximation algorithms, and the PCP theorem was the final piece in a project to unify these two strands of complexity theory, and today it is taught everywhere in the world as a single theory and a pretty strong one. So thanks to the PCP theorem. So besides complexity theory and the very fundamental P versus NP problem, on which Madhu contributed in very significant ways, Madhu is also known for his deep contributions to coding theory, which gives foundations to the reliable communication, which is essential for today's technology. He's recognized for introducing new concepts, such as the concept of least decoding in coding theory. And today he is going to tell us about the many interesting ramifications of the theory of communication. So please join me into welcoming Madhu Sudan.
Thank you, Albert, and thank you, Luis. I hope I'm audible. I'm delighted to be here, and I'm really sort of thankful for this coincidence that puts me here on the same event as this very important occasion for CRM. My first visit to Barcelona was roughly 25 years ago, again, organized in part by the CRM, where I visited a semester on the probabilistic method that was held at the University Autonoma at Bellaterra. So it's been a long time since I've been here, and actually, unfortunately, in between there have been no visits, but it's wonderful to be back here in Barcelona and see everybody. In addition to this lecture that I'm giving today, I had the pleasure of interacting with colleagues and students of this field over the last 2 or 3 days, and I'm just delighted to see the kind of talent that's here, and I'm looking forward to seeing many more interactions and many more of your scientists. Albert, by the way, is a personal role model, has done amazing work in the field, and I'm delighted that I had so much time to chat with you. Moving to today's talk, I'm going to talk about mathematical theories of communication, old and new, and I'll try to explain a little bit about what we want to do. The communication for today's talk is going to be all about digital communication. So when we are transmitting letters of the English alphabet or bits or something else. And this is a challenge that arose in the 1940s when we suddenly realized we had the technology to be able to actually communicate digital information moderately reliably. And now the question was, how can you make it really reliable? And what is really reliable? The challenge for such theories are that communication can be expensive. You think of a satellite sending messages to the Earth. I mean, it cannot use up all its battery on just communicating. It can be very noisy because physical media are always noisy and we have to use physics to communicate. Modern theories also get challenged by more additional complications because communication can be interactive. I'm sending you some message, you send me a message back. But your message is presumably responding to my question. If that's the case, if my question did not get accurately transmitted to you, when do you spend time to discover this was an error, and when do you invest time in exploring the past, and when do you get to the future of the rest of the communication that you have to do? And finally, communication is very, very, very contextual. It depends on operating systems that my phone uses, that my machines uses, but also when humans communicate with each other, we are always relying on common language. And by the way, thank you all for accepting my lecture in English. Unfortunately, my Spanish is bad and Catalan is 0. So, well, actually, both are 0. So, so now comes the question. So that's communication. We're going to be talking about digital communication and reliable communication. Why do we need a theory? I mean, my phone is working and it is communicating with whatever servers are out there. They are managing to communicate with other servers out there, and they eventually reach any emails that I want to send, a WhatsApp message reaches you. Why do we need a theory for all this? And this is a good question to be asking in an event like this. Why do we need mathematics when engineering is working fine? The problem with ad hoc solutions is that they work today, and we have no guarantee that they will work tomorrow. Guarantees come from theorems, and we need to prove theorems for this. Formulating a problem will often allow you to say, look, here's a problem statement, there can be multiple solutions. Very often in the world of engineering, you hear of the problem by its solution. We cannot accept that. We must distinguish at least these two. I mean, this is a very, very basic message that we try to tell all our students, but it still takes time because they've been trained with this methodology where you say the algorithm is the problem. No, the algorithm is the solution to a problem. And there are many other such instances in mathematics where we should first state this problem. That will allow us to think about different solutions and compare them, but it will also allow us for some creative solutions that you might not have envisioned because you didn't specify the problem carefully enough. And finally, understanding limits. Some things are achievable, some things are not. When it is not, it is good to realize these are the limits and spend your energy and money elsewhere. And limits are some things that you can get only when you have a theory. So this is why we need theory. But why do we need many theories? Why was the old theory not good enough? And I will start with an old theory going back to Shannon from 1948. But you might then ask, okay, so the reason you're coming up with new theories is because that one didn't work. And the answer is actually quite the opposite. Shannon's theory has been immensely, immensely successful. Successful not just as a mathematical enterprise and as a launching pad for mathematical enterprises, but also every step in engineering that makes our phones communicate, our computers communicate, our wires capable of carrying digital information, our magnetic disks store information, they have all relied on this theory and built on top of it. So it's actually quite the opposite. It's a very, very good theory. It's become so successful that it's sort of like we've got off from the ground level and moved into orbit. And now there's much more possibilities that we can think of. Possibilities that were just too far into the future for Shannon to be investing his time and the next generation of scientists to be investing their time. But it's time for us to start exploring them. And those are the kinds of questions that I want to get to later today. So let's, however, start at the beginning. For us, beginning is 1948, really. So this is when Shannon's seminal paper was published. The problem was that of digital communication, and the reason digital communication is hard is because of the following kind of an error that happens. It's not a lot of error that happened in the transmission of information, but it was significant enough that we lost the most important piece of the message. And when you're transmitting digital information, you never know which piece of it is the most important one. So in this example, there's one letter that has been transposed and it completely changes the meaning and can have catastrophic consequences if it is left uncorrected. So we do need to protect information from errors. And unfortunately, communication media, any medium of communication that you can design is always going to be noisy. The goal over here is never to make it noise-free. It's always to make it less noisy than what you start with. And we want to go from the scale of saying, oh, there will be an error every microsecond, to saying there'll be an error maybe at most every month, or things along those lines. So this is all we can hope for, and that's the kind of theory that we want to build. How can you build reliability? And now I'm starting this talk, by the way, I know we're all mathematicians here, but at the same time, I think there's enough diversity in the audience that I did not put in very, very detailed proofs. Definitely not. I did not even put in very detailed theorems, but almost everything that I say is accompanied by a theorem somewhere, someplace. But I will give you some ideas along the way, and this is one of the first simple ideas. Well, how can you build reliability into communication? And this is probably what people were thinking of in the 1940s. You store any piece of information that you want redundantly. What does redundantly mean? Many times. So if I want to say we are now ready, I say, the W 3 times and the R, 3 times, etc., etc. Noisy transmission of information will still flip some of these bits. And now we've sort of illustrated in this brown where the errors have happened. But of course, as a receiver of information, you should be colorblind. and just say, well, what I'm seeing is a sequence which says WXW, EEA, ARA, etc., etc. And the way you would correct information over here is by saying, oh, let's look at the most common symbol in every block, and that's probably what you sent. This is good, but not great, as already in this example we are seeing that, oh, there was this one block which got, incorrectly recovered. So this is the level of mathematics that I'm going to do today. So as the number of repetitions grows higher, the reliability of this transmission scheme gets better. As the length of the transmission gets longer, the reliability of this communication scheme gets lower. In order to find a sweet spot, the number of repetitions should somehow grow with the number of with the length of the transmission, because these two forces are acting against each other. Okay? Now, I'm not going to prove the exact quantitative dependence, though of course many of you probably know how it goes. But it's clear that as the length of my messages gets longer and longer and longer, the amount of repetitions also of each symbol is getting longer and longer and longer. And that's not such good news, because we are scaling extremely, extremely rapidly. And so everything has to be repeated too often. So this was probably, and I don't know, I wasn't there either, the state of thinking in those days, that yes, this is the inevitable thing. What else could you possibly do? So any scheme must have the rate of communication. How much is the actual number of messages that you are sending versus how many times we are repeating it, or what is the total length of the combined message that we are sending. This ratio has to go to 0 as the length of the message going to infinity. Shannon's theory came and completely turned the picture around. And many people look at the very fine details of Shannon's theory and say, oh, this is where the most interesting things happen. But to me, very, very, very interesting things happen already at this qualitative stage, where we suddenly said, no, the amount of repetition, the redundancy does not have to scale with the length of the message, with the length of the transmission. It can be some fixed constant. It depends on how much error there is in the system, but not on how many bits you are transmitting. In fact, the story is even better, and let me get to that. In order to get to this point, Shannon in 1948 proposed a remarkable system which said, before Alice sends a message to Bob, before Alice sends this message, she is going to compute some function called the encoding function, which will take a small amount of information and make it much larger. So encoding is expanding the length of the message, adding redundancy. In the previous example, it just said repeat every letter 3 times, but we can do something else maybe. Shannon also said, let's use a decoder at the other end, which does the equivalent of what we did block by block, taking majorities. But now again, you can use a general function. Why is this such a remarkable thing to put these two boxes? Because these boxes were not sold in the stores in those days. The encoder and decoder are computations. These are some functions that you want to compute. But we had no computers in the market. In fact, one of the challenges, one of the things that people were aspiring to was to build computers in the future. So if he had been restricted by what was available, he would have never made these steps of progress possible. But he wasn't. He just went ahead and said, okay, look, let's just put in this abstract object. I don't know where they'll come from, but maybe somebody will manufacture them later for me. And let's just look at the mathematics. The encoder is just a function. We'll call it a function from, say, k bits for simplicity to n bits. So this is expanding k bits to n bits. The decoder goes back from n bits to k bits, but in between the channel has introduced some noise. Okay? And the rate of the information transmission, this is what we want to minimize, is this ratio k over n. We want k divided by n to be some constant which does not go to 0 as n goes to infinity. Previous example we saw had that constant, had that ratio going to 0 as n went to infinity. Okay? Can we get some of these things? What is the requirement? This is where we are specifying the goals of the system. it is that when you encode some information according to this process, you started with a message M, you encoded it, the channel added some noise to the signal, then you decoded it, and we are hoping that you get back the message with very high probability. Okay? That is our hope. Can we do this? What kind of parameters can we achieve? And what are the best encoding and decoding functions? Shannon asked this question in those days when no E or D could have actually been, no really interesting E or D could have actually been built. Maybe repetition and majority logic could have been built in the hardware of those days. Anything beyond that was inconceivable, but he went ahead and asked this question anyway. Which are the best functions E and D to use over here? He gave a beautiful theorem, the Shannon coding theorem, and it says the following. If in this transmission of information, this noisy channel, all it's doing is flipping every bit independently. Okay? So simple probabilistic model, every bit is flipped with probability p. So if I send a 0, you will receive a 0 with probability 1 minus p, and a 1 with probability p, and the same kind of a flip happens if I send a 1. And every bit that I'm sending is going to be acted upon independently. There is no memory in the channel, there's no stability or anything. Then you can achieve a rate of 1 minus the binary entropy of a function of the parameter p. The binary entropy is written down over here in an explicit form. The exact formula is not important to us today, though it's of course, a very, very profound and important formula has been noticed by the literature later. And he also proved that this was the best possible. You cannot do better than this rate. Is this an interesting number? Let's look at some examples. When p equal to 0, that means whatever I send is accurately sent to you. There is no probability of flipping. Then you don't need to do anything. You don't need all these sophisticated architectures. You just send the information and the receiver has it. The rate of information transmission is 1, should be 1, and that's exactly what this formula tells you. The entropy of 0 is actually 0, so the capacity is 1 minus 0, which is 1. So you're transmitting at 100% rate because this channel has no error. If p is a half, which means if I send a 0, you receive either 0 or 1 with probability 1/2. I send a 1, you receive a 0 or 1 with probability 1/2. What you receive is independent of what I'm sending you. You don't need the communication channel to simulate what you would receive. Okay? So there is no communication channel in this case, so the capacity is 0, and indeed this formula translates to 0. These are the uninteresting points, but the important thing is in between this formula, 1 minus entropy of p, is a monotone decreasing function. It goes from 1 to 0 continuously. The most important points over here are something just a little bit to the left of 0.5, 0.499. If p is 0.499, there is still some capacity in this channel, and this is fundamental to satellite communication. A satellite goes off into space, you're sending information back to Earth with a low power battery, and the signals are interfered with all over the place with cosmic radiation, but the signal that you're receiving has some correlation with what was sent, so there is capacity in the channel and you can use it reliably. And the amount of blow up you have to do is just a constant factor. It's not dependent on the length of the transmission. So this was a remarkable result from Shannon, and here are some highlights. I mean, this solution, how was this rate achieved? Shannon used the probabilistic method. He said, pick an encoding function at random, and I will prove that it actually satisfies this property. He also proved the limits. You cannot do any better. This is like remarkable, so foresightful and so forward thinking. So the architecture, the analysis, independent discovery, more or less, of the probabilistic method. I don't know how independent it is. There are no citations suggesting one depends on the other, but that doesn't mean that they might not have been aware of each other. So in particular, Erdős had been popularizing the probabilistic method at around this time, we have no indication which suggests that this method depended on knowing that other tool. And there are deep mathematical discoveries. The notion of entropy, which can be quickly translated into a measure of information, have become profound tools in mathematical analysis today, and it goes beyond mathematics into many other fields. And the initial theory was highly non-constructive. So, when you started picking encoder functions at random and decoder functions are brute force, these are not very constructive. You cannot go out, build a computer which computes these functions easily. But today, with lots and lots of tools thrown in, algebra is useful, algebraic geometry is particularly useful, graph theory, information theory, algorithmic theory, combinatorics. So many different aspects of mathematics have gone into this field, and pretty much everything we know from the theory is now done constructively. So we can actually go out and build physical devices which match the theory today. So that's amazing things. Shannon, by the way, in this seminal paper also had this aside, said we can approximate natural language by a series of simple artificial languages. So he's really developing a theory of how to apply probability to capture so many elements of communication, and language is an aspect of communication. So he introduced this so-called ith order approximation. So you look at I-1 symbols that have just appeared, compute the distribution of what the ith symbol might be in any language based on this, and then he applied this to English. He did it by hand in those days and said, oh, this is a third order letter approximation. So, doesn't look like English, but it's not like, demonstrators could have been a word in English if, a community had chosen to go that way. Reptagin might be an animal, who knows? But these are like very plausible sounding words which are just being generated by letting each fourth letter depend randomly on the previous three letters. Okay. And then he did a second order word approximation. Now here you look at two words and then generate the third word and so on. And it's also looking pretty reasonable. This is what large language models are doing today. And the only thing is they have a little bit more memory than Shannon did and a little bit more computing power, and they're doing pretty well. And Shannon actually had a very interesting empirical observation. He said an ith order approximation actually produces sentences of length about 2i, which are very reasonable. That's kind of something interesting happening with language, right? Excuse me. So this was Shannon's profound theory. And I want to turn to other theories that have since followed. Shannon's theory is, really, like I said already, it's universally helpful in technology today. So there's no question about that. But because the technology today is doing so much communication, we keep asking for more, there's more theories that are needed. I'm going to talk to you about three different vignettes over here. First of which is communication can be interactive. Okay? So for example, if you're doing some distributed file sharing, then I do some edits and send the edits to the server. The server updates my file. And after a while, maybe like once in a day or something, I'll say, okay, let's download the whole file and let's see what it looks like. But in the meanwhile, I'm just doing some basic edits. What if the interaction suddenly lost one of my edits and then continues with the rest of them? I could get a completely different object. I say one symbol saying, oh, I'm currently inserting, and then the next sequence of sentences are going to be what I'm inserting, but the message which said I'm inserting has been dropped, and instead everything that I've said after that is a control command, and it's going to destroy files, and it's going to delete words, going to inject words, while I just mean to say insert these characters. So interactive communication is ubiquitous, but also very unreliable due to errors. How should you correct errors in this setting? So when should we start working over here? So Schulman, a remarkable scientist in 1992, came up with this beautiful paper completely out of the blue. Nobody was really thinking about it seriously in those days. Came up with the question and the answer a first answer to this question. Since then, after sort of a long period during which the paper just sat in the alcoves, people picked it up, and now there's a very compelling theory matching almost that of Shannon, not as close, but pretty good. So here we are looking at this, say, for example, the server-user interaction. So we are doing interactions going back and forth, and we want to make sure that the entire sequence of bits that were transmitted from the user to the server and back are all being communicated faithfully. Okay? This is what we want to be able to preserve. So, on the one hand, if there is an error, I must detect it immediately, because if I don't, then all the future communication is all, if I've just asked you a question and you don't understand the question, you probably want to understand the question first, make sure that you got it right before you send me a long answer. On the other hand, how much time if you keep asking this question, oh, was this right? Oh, and then I say, no, okay, here's the second aspect of the question. You say, oh, is the first part right, and the second part right, and the third part right? We keep going back and looking at the entire history of communication and keep checking it at every moment of time. This is going to be extremely wasteful, and once again, we will lose this feature that in order to deal with some small, tiny fraction of errors, we are going to have to let the rate of the actual interaction go to 0. And this was, again, a worry in the Schulman era. Must it be the case that if you have interaction, suddenly you lose this benefit of saying, it doesn't matter how long the interaction is, how many bits are totally transmitted, as long as the errors are small, under some fixed constant %, the amount of redundancy is also a fixed constant %. And redundancy is not as simple. Who inserts the redundancy? Me as the question asker, or you as the responder, or both? So it's very challenging as a question, and really if you set this up mathematically, it becomes a beautiful question. Also seems like a completely intractable question. Thankfully, Schulman and other researchers were able to give very nice theorems. So in particular, you could ask the same question. If each bit is being flipped with probability p independently, not even by an adversary, what is the rate at which we are communicating? And it was, again, not clear that you could achieve a constant factor of redundancy would satisfy this thing. The limit is not as well understood as in Shannon's case. So in particular, we only know something like, yeah, if p is less than or equal to 1/8, then you can get some positive rate of communication. But if the error probability is a little bit larger than 1/8, we don't really know the exact limits. These have to be calculated a little bit more carefully. But we do know that it does not scale like 1 minus the entropy. It is 1 minus the square root of the entropy at best. And this square root is roughly the right behavior, but we don't know that for sure. So a lot is known, but not everything. And the players over here, it's a beautiful series of works by Schulman, of course, the starting point of this series. Braverman and Rao sort of picked up this paper after 15 years and suddenly realized, we can start getting quantitative limits out of this. In particular, proved that this p less than or equal to 1/8 is the right answer. Cole and Raz are two remarkable computer scientists who've started exploring this question and realized that 1 minus square root of entropy is the right feature. And Heupler is a new figure who's been contributing remarkable ideas to this sequence of papers. I would consider this, I'm not just exposing the mathematics of these questions to you or the solutions, but they are beautiful solutions. These are solutions, these are accompanied by theorems. These theorems are rock solid like every other mathematical theorem that we know about. And I think they're surprising even given the wonderful and very surprising theories of Shannon. Just because you know Shannon's theory doesn't mean you will get anywhere close to this. These have to, really, they force you to open new creative hats and solve problems. Okay. That's all I'm going to say about this particular theory. And now I want to move to more modern things. So like I said earlier, communication is interactive. So now I want to consider a slightly different example, like I want to buy an airline ticket, okay, like I did when I'm coming here. Now, in order to buy this, decide which is the one ticket that I want to buy. I want to go to a travel agent, maybe, and ask them what are all the flights that you have and all the different features and worries and bugs and so on. And the travel agent wants to know all the constraints that I have, and I don't like traveling in certain ways. I do not like to make stops in certain places. I don't like to have overnight flights which have a stopover in the middle of the night. God knows how many constraints I have. God knows how many airlines and options the travel agent has. These are very huge pieces of information on either side. And if the only mode of communication of being able to buy a ticket was I do a core dump and explain every one of my needs to the airlines, I mean, my airlines would be worse than my therapist. So they would have, deep insights into my behavior, but maybe still not an airline ticket. And vice versa, I don't want to run an airlines and their systems management. They have infinitely many options, well, close to infinitely many options as well. So I don't want to do that. So we want at the same time to find a quick compatible point in the middle, something that says this is what I want to buy. How can we model these kinds of challenges? Is there a model? How much of my context should I share with the airline? How much of the context should the airline share with me? Even independent of issues such as privacy and secrecy, which are definitely important, but I'm setting them aside today. Just to say, look, I don't want to communicate forever. How should we do this right? How should we study these problems? And this is the exact class of questions which was actually raised by Yao, Turing Award winner, who's now in Tsinghua in Beijing, who set up this class of problems called communication complexity. In communication complexity, the central object is this function f over here. It depends on two inputs, x and y. X, which is known only to one of the players, we'll call them Alice. The other is y, which is known only to the other player, which is Bob. So Alice might be the traveler, Bob might be the travel agent. X is all the information that Alice knows about her preferences and priorities. Bob is information y, is all the airlines that flights that exist and their timings and their prices and whatnot. Okay? You want to take these two together, and f is the function which says, given the preferences and x, this is the airline you want to travel on. Okay? Question to us, do we really need to send all of x over to from Alice to Bob? If you do that, then Bob, with knowledge of the function f, can actually figure out what's the best option. Bob can also send all of y over to Alice, and then Alice can figure out what's the best option. Question is this something in between that you can do? Is there some way in which we can communicate less than sending all of x and all of y and still be able to compute f of xy, determine the value of f of xy? Okay. Now, in the airline example, it's not trivial to think of a good protocol. But it turns out there are very good ones, and I'll sort of hint at them later. So we want to minimize the total amount of communication that goes on, and this communication can be interactive. Alice might start by saying, I want to travel on a Sunday or something like that, but we have to figure out what all needs to be communicated and how. The communication complexity we measure as the number of bits that are exchanged to compute this function f. And we should be able to do this for every choice of x and y, or for maybe x and y chosen from some probability distribution. We should be able to do that. Okay. So this is the concept of interest. And we can do lots of variations that we might allow some common randomness to sit between Alice and Bob, and this might accelerate things. So maybe both of us have access to an English dictionary, and we just use it as a source of random bits or something. Something like that. We may have some common information, and there may be other contexts. I mean, maybe everybody knows that maybe end of August is peak holiday travel time in certain parts of the world, and so tickets are going to be expensive, et cetera, and both the airline and the user might know this information and use this. Now, this model was introduced by Yao, but I don't know what his intentions were. but very soon this model got hijacked to prove things cannot be done. Here is a function f, and by the way, Alice has to send all of x. Here is another function y, and Bob has to send all of y. I mean, this, if you look at the entire, if you open a book on communication complexity, you will see model, chapter 1, lower bound 1, chapter 2, lower bound 2, chapter 3, lower bound 3. All of these are proving nothing interesting happens. That's not the real truth. There is everywhere in between, there will be a counterexample to a conjecture saying, oh, this lower bound cannot be proved because there is a nice communication protocol out there. Let me tell you what those things actually say. There are some very interesting protocols out there. So, okay, let's start with a very simple problem. Let's say Alice has n bits of information, x1 to xn, or n real numbers, it doesn't really matter. Let's take real numbers, okay? And Bob has n real numbers, and think of these as small integers or something like that, just to keep things finite. And maybe they want to compute the sum of the differences of x and y. Okay? This is not the hardest of problems to want to solve. We want to say somehow that, oh, you don't have to send all of x1, x2, x3, x4, and so on to xn. You can do something better. Some thinking will reveal to you, yeah, of course, we can do something very simple. Bob can send the sum of x1 to xn, which he can calculate, to Alice. Alice can send to Bob the sum of x1 to xn, and Bob sends back that sum that Alice sent minus the sum of the y's. We used commutativity or something of associativity of addition or something to get this to work. It doesn't sound like rocket science. This is all you can do. So here is a slight variation on this question. In case you're wondering why have I repeated everything twice, well, actually I put a little bit of a hitch here. x1 minus y1 squared and so on up to x1 minus xn squared. What am I doing now? Now you should really think of Alice as having a point in n-dimensional space, Bob as having another point in n-dimensional space, and we are trying to measure how close we are. This is a little bit closer to the airline example. I might say, I can take the information that I have and say, if I am given the following air flight option, how much would I like it? If I'm given that option, how much would I like it? If I'm given this option, how much would I like it? I want to know, is there some point that comes close to Bob's options? So these are like, starting to look like these kind of problems. This is the simplest of the problems I can ask. And now you can ask, can you do this very easily, effectively? This is the only other proof that I will do. So I have like 10, 15 minutes maybe? Yeah, okay, 15 minutes. Sounds good. So let me just at least do this one. I will not give you any proofs, of course, but let me tell you the protocol, which is not very far from where we are. This is the whole protocol. Alice and Bob use common randomness. Recall I said, oh, if you want, you can assume common randomness. I'm going to use that common randomness now. Let's say they have n bits which are random, and a bit is either a number plus 1 or minus 1. Okay? So, and both Alice and Bob know R1 to Rn, and they're going to use this to calculate this function. Alice will first compute the sum of the squares of the xi's, and also compute the inner product of the r vector with the x vector, summation of ri xi over all the i's. Two numbers, and we are pretending all numbers are small, and let's say there's a small number, and she sends them over. Not n things, just two things. Bob computes t, which is y1 squared to yn squared, and t2, which is the summation of ri yi. He also knows ri, he knows only yi, so he can compute these things. And the remarkable theorem is, if you look at the expectation of R1 to Rn, when these variables are randomly chosen from plus and minus 1, of the quantity S1 plus T1 minus twice S2 T2, this is exactly the quantity that we want. Okay? So once you have a random variable, which is an unbiased estimator of the quantity you want, you run this experiment many times, choosing many Ri's. You'll start to converge, hopefully assuming the variance is small, and in this case the variance is small. So this is the protocol. So you can not only just, compute differences of numbers or something, but very sophisticated things, with some shared randomness. And this is not the only example. This is a page where I had many more examples of things which can be computed very easily with communication complexity using common randomness. And many problems sort of fit in this framework. So the moral of the story, and this is the unstated philosophical contribution of Yao, is when you have a focus to your communication, the goal of the airline and me is not to have a deep, all-encompassing chat. It is just for me to buy an air ticket that I'd be happy with. When I have this goal, and when the airline's goal is to sell me that one ticket, there are better ways of communicating than just doing core dumps on either side. We can have very, very effective methods of communication. Indeed, if we apply it to the airline setting, I think we could sort of convert the protocols that I've described in the previous page to really get communication protocols where the total amount of communication between the airline and the traveler would be twice as long as describing the final itinerary. Now, that's not a huge price to pay. I mean, itinerary has to come to you anyway, and you want that. Well, twice as long, as much communication, and you would be actually exchanging all the information that you want. The only thing that it assumes is that somehow you express your preferences as vectors, somehow airline describes its offering as vectors, and proximity of these vectors is what determines how matching, how things are matching. And this is not very far away. I mean, the machine learning theories today are expressing everything as vectors, and preferences along these lines are pretty much exactly what they are modeling most of their objective functions as. So it's not really very far-fetched as an idea. Okay? All right, so this is my second new theory. Finally, I want to talk about a new theory that I am personally involved with. Up to now, almost everything that I was describing was existing theories that I might have worked on. But this is something that I care about. And this comes back to this question. You know, Shannon's theories and every other theory of communication that's been built so far is very strongly prefaced on the assumption that the sender and the receiver have perfectly agreed on the communication protocol. We may not agree on what our inputs are, and that's why there is divergence, but communication protocol is completely determined. And this is just an assumption that is so violated in so many of the communication settings that we see that we have to start building a theory towards that. What are some examples? Like this talk is an example. I am giving you some bits of information. What are these bits of information? It is not everything I know. It is not prefaced on everything that you know. It is some estimate of what I think you may know and what you think you may be interested in. And furthermore, I'm also making some assumptions on how much of English is common to us and how much of mathematics is common to us. So all of these are assumptions. They're never, I mean, we didn't write a contract. I mean, I had a contract saying this talk can be videotaped, but there was no contract saying this is the English that I'm allowed to use. And so where is this perfectly agreed communication protocol, context in this conversation? It's not there. And yet, if I didn't assume all this knowledge of English, we would not have, I mean, you would not be gaining anything. Maybe you're not already now, but I'm hoping you are. But if I don't make use of this assumption, I'm not going to get through. Can we model all of this mathematically and ask questions realistically about it? And I'll sort of skip this one slide, though it's a fun slide. So there are two aspects to learning to communicate that I want to emphasize. One, when a child grows up and learns a language, how is it learning to communicate? It's learning by communicating. You can take the same child and place it in different parts of the world, and it would have learned different languages. It's not like the language was hardwired into the child by their parents. It is because it's in that environment. And in that environment, what are its inputs? Well, other communication signals, and maybe some physical signals like milk. But it's largely signals that's coming in, but they teach you how to communicate. We don't have that with computers. And with Goldreich and Juba, we tried to write a paper about how you would communicate in these cases. And we prove a theorem. What I put down in quotes over here is a theorem. The hardest part of this theorem was, of course, trying to come up with the definitions that make it sound like this is a mathematical precise theorem. And what we prove over here is that you can actually assume no context and start to get meaningful communication across, provided the communication is useful to you. I mean, you can learn to speak provided the communication is useful to you, but not just useful, you should be able to verify that it is useful. And these are notions, verification, utility, etc. These have been made mathematical in the past. So we can capitalize on all of these mathematical definitions and actually make a theorem out of it. So I encourage you to take a look at this to see how it goes. A different issue that we talked about is all this context in communication, how much of language can I assume, how much can you not assume? And we tried to model this also. This one gets modeled very nicely inside the Yao framework, but it looks like a variation which also fits inside the framework itself. So when you talk about communicating fn, some function, maybe if we make no assumptions about shared context, the amount of communication that you have to do is going to be a lot. But now if you start making some assumptions about a shared context which is perfectly shared, the communication shrinks a lot. Okay, so maybe context is, what is the name of this function? What is the randomness we are using? What's the distribution from which x and y came? If you start making these assumptions, maybe you can get perfect communication, very, very little communication. Most of the communication vanished, a tiny amount was left. Once you have this formulation, you can ask the question, what happens if these two are not equal but close to each other? So maybe Alice has some interpretation of the randomness, Bob has slightly close by string. Maybe Alice thinks the function we're computing is f, Bob thinks it's some function g, but they're very similar functions. Maybe Alice thinks that the distribution is something, Bob thinks the distribution is something else. All of these are questions that you could ask. And what you can hope for is that once you sort of have only small variations, the amount of communication only grows a little bit. Not as much as if you drop the entire context, but not as little as if you assume perfectly shared context. Are there communication protocols which satisfy this kind of a graceful feature that when the context goes from being unequal to being close, the amount of communication only grows by a little bit? We tried to explore this in various mathematical settings and came up with lots of theorems. I won't be able to tell you about this, but lots of works over here that explore these questions and lots of results over here. Okay. Some of the examples are, if I'm compressing information and I want to send it to you, almost everywhere this question is studied, the assumption is you and I must have agreed on what is the distribution from which this thing is coming from. But, all the information that I know about communication I'm compressing into this talk, but you and I did not agree on a distribution. So we have to have something better than that. We showed that you can actually get a lot of the mileage of compression even when the distributions are not identical. And by the way, in case you think maybe this should have been obvious, let me say that we only know how to do this using some randomness. And if you want to get rid of the randomness, there are wonderful mathematical questions that pop up that are not answered, combinatorial questions that have not been answered. We can design, how is a dictionary designed? I think Luis told me that the design of the Catalan dictionary belongs to this building. Okay, so sometimes it's designed centrally, but most dictionaries that we work with in practice, any human being has the ability to inject a new word and suddenly everybody adopts it and other words don't get adopted and drop and die. Dictionaries are distributedly produced, and the rate at which we learn the new dictionary is different. There were about 10 years during which I did not understand the meaning of the phrase "my bad" when all my students were using it and I was correcting them and saying, no, you mean my mistake. And I said, no, you mean my bad, because that is the new phrase. So dictionaries are not centrally agreed upon. They're always, we come up with them as an emergent phenomenon. Can we model the use of a dictionary that emerges like this and see how well it will behave? You can study these questions. So I won't say a lot, but I do want to say a little bit about this emerging theory. So one paper that we did was we said, well, can we do an information theoretic study of language? And what is language? Well, to us, language is just a way of expressing something that I want to say in as compressed a form as I can. So it's really, compression is a mathematical analogy of our communication problem. We just want to, compression has a dictionary, language has a dictionary, and they play exactly the same role. They tell me, given a message, how do you say it? Now, and of course, in both cases, the goal is to keep the communication short. So it seems a lot like compression to make this, compression can be used as a proxy for studying languages. And then when you ask the question, is the frequency of words known globally? Well, of course not. And so that's equivalent to saying the distribution is not perfectly shared. And moreover, like I said earlier, everybody can sort of propose new amendments to the dictionary, and so the dictionary keeps evolving in some distributed, decentralized process. And you can study pretty much all of this, and in this third paper over here, we actually study how a dictionary may emerge from compression, because we don't want to study language which has other eccentricities, but compression we can study. And when different people are learning the distribution by independent samples, how they can all collectively emerge at the same coding dictionary, which will achieve very good compression. So we can prove theorems along those lines. So I'll wrap up with a couple of slides. First, we just saw theories of communication. It's a sampler. It's not exhaustive. Every person you go to working in a field like mine will have their own favorite theories, but these are some of them. But the very interesting thing is there are many, many surprises here. And every time you turn to modeling a problem formally and then specifying what your goals are, you can come up with very interesting solutions, and sometimes also limits which say, furthermore, other solutions will not exist. There's still a huge divergence, in my opinion, between the theory of design communication, which is what every object that I'm waving at right now relies on, and the kind of communication that humans practice. And if we can get the kind of communication that humans practice also to be automated, it could be a vastly better communication system. On the one hand, the systems are supposedly getting very, very intelligent, but at the same time, when it comes to communication, they have the most miserable of breakdowns. And that's because of an deep and inbuilt tension between, not between the two persona, Turing and Shannon, but between the two theories that they have created. The Turing theory really says you should go program your computer and let it do whatever you want. The Shannon theory of communication says don't change those communication devices. Their protocol should be hardwired. We cannot have these two theories coexisting, so we need more new models over here. And finally, I think of communication as really a lens. There are so many phenomena in the world where the only way we can try to understand what's going on inside a black box is to look at it from outside and say, what is it telling me and what can I ask it? And the Turing test is a famous example of this lens of communication. We want to know, are computers getting intelligent? That was Turing's supposed claim. And the way he said that you will tell them is by sort of just interacting with either a computer or a human being and telling which one you're interacting with. This is a test built on the lens of communication. And the lens of communication is one of the most powerful lenses that we have into exploring other systems that live beyond us. And this is something that's, I think we need to understand communication theory better so that we can apply this lens better. All right, so I think I'll stop over here and take questions.
So we have a microphone for questions in some time. Yeah, there's a question here.
Thank you. Thank you for this beautiful lecture. How do you deal with semantics in general?
That's a great question. How do we deal with semantics? It's, I think semantics, we should view it as a tool in an arsenal, not the sole purpose. We should definitely incorporate every way in which we have abilities to capture languages in communication, and semantics are giving us some of the most expressive ways in which we can capture large swaths of what we do understand. The problem with semantics that I feel, and that we still need to deal with, is when we allow communication to be flexible and for each entity to inject their own words, their own languages, their own variations, then we want to also allow for the semantics to have exceptions to it. So semantics could be the core of the theory, which keeps it short and tidy, but you should always be willing to explore outside any prescribed rules, saying that, look, because we are working in a decentralized, distributed system, we should expect some variations which will not follow the rules. And if we do that, I think we can, leverage this very, very well. Does that help with the question?
Any other questions?
Yeah. My question is a historical one. I wonder whether John von Neumann had a role in the beginning of communication theories.
Oh, that's a very good
question. Did von
Neumann
and Shannon communicate each other?
Good. So that's a very good question. Unfortunately, you have me there. I don't believe, in all my explorations of information theory and coding theory and looking at the papers, I never saw a concrete paper by John von Neumann on this thing. There is, of course, the fact that if you're looking at an overarching theory of communication, you have to allow for players to have incentives, and then game theory enters the picture. And of course, John von Neumann had fundamental contributions. I cannot ever separate communication from computation, ever, totally. And of course, once you start thinking about computation, John von Neumann had a role. So there have been he's been surrounding the area in various ways, but as far as I know, in the core communication literature, I don't think John von Neumann had a role. Okay? That's just I'm just admitting what I know and what I don't know. I'm not necessarily saying this is the truth. Yeah.
Any more questions? A question myself, if I may. So you mentioned that you don't know exactly what the purpose was for communication complexity when Yao introduced it. So one guess would be, maybe you can correct me otherwise, that he wanted to develop a model where he could actually prove lower bounds and prove limitations beyond the communication model. Now, as you said, when you open a book on communication complexity, you see all sorts of lower bounds and it's been hijacked. But it's a bit surprising because in the other theory of the theory of computation, we don't have lower bounds, right? We don't have methods for lower bounds. So in communication complexity, we started with very basic methods like combinatorics and so on, and then we went back to using information complexity. We used back again information theory to prove lower bounds. So is there a chance that this can actually be used for the theory of computation and make progress finally on the big problems?
Good. So that's a very sort of a deep and broad-reaching question. So I would agree with you that Yao was very much interested in concrete tools that allow you to prove lower bounds. And in fact, we do know a little bit more about why Yao introduced this model. We've talked to him and so on. On the one hand, the paper is titled On the Complexity of Some Problems in Distributed Computing, which sounds like, two players separated and they're trying to compute some function. So we really are trying to build a model for this. But it was almost definitely the case that he was interested in proving computational lower bounds, trying to say that circuits that compute certain functions must be very large, And the idea, I think, that was in his mind was if you sort of tease the circuit into two parts, there must be a lot of communication going on between the two sides in order for us to be able to compute the function. His theory didn't immediately lead to that, but then later works like Karchmer and Wigderson actually formalized this example completely clearly in a nice way. Yes, so yeah, Yao definitely had lower bounds in mind, and in particular, he thought, I think it was the early stages of this lens of communication. By studying how much communication is needed at various stages of computational processes, we can try to lower bound the amount of computational resources needed. This might have been an ambitious goal at the time. As to whether we will use this, I mean, there are concrete reductions like the Karchmer-Wigderson game, which tell you that if you can solve problems in this field, then you will be able to solve problems about computational complexity, things that don't seem related. But unfortunately, it's equivalent, and so it's turning out that the communication problems are hard to solve also. So yeah, there's a possibility, but I don't know that I can start taking bets on it.
Okay. So any more questions? Yes, there's one more question. Can you bring the microphone?
And I'm interested in applications to biology. So the question is rather simple. If those theories, they've been applied to communication a little bit beyond human interaction and computer devices, let's say, I don't know, because there are communications everywhere, let's say between cells, electrical circuits, and all related. So just that.
If maybe you can repeat that question one more time, just so that I answer.
Yeah, sure. So if those theories, they've been applied to systems which, for example, some other biological system, let's say something that is not human interaction and communication between digital devices.
Right. So in principle, we should be able to apply these kinds of theories to all kinds of systems, in particular to understand what's going on in a cell by looking at the communication with the cell. This was an interesting idea that was proposed to me by also by some molecular biologists in India once when I visited, and we never managed to pursue it. There are challenges everywhere. It takes us, at the end, you can build a very nice theory. I mean, the theory that we're talking about over here can be applied to whale communication and understand what the language is. You can apply it in many places. The challenge is always the amount of data that you have and the amount of computing resources that you have. And if we have enough data, which I think we can hope for in cellular settings, we need three things. One, lots of data, lots of computing power, but the third is a bit of luck, which involves the underlying model being actually simple. If the underlying model is not very simple, we probably don't have much hope. I'm pretty optimistic that in many of these cases we will be able to understand what's going on in the innards of a model, even if we don't say exactly how it's doing something, to be able to simulate something else which does exactly the same things, we are not very far away. I mean, large language models are already getting to that stage. So I think it's very possible, and what we've learned from the Shannon theory is if you can start predicting, then very simple next step kind of mechanisms, then you have vast power in predicting the whole behavior.
Thank you.
Sure.
Okay, so as you can see, Madhu Sudan is a very deep thinker, and he has thought of all sorts of problems, and he has made great contributions, so I think we should thank him for coming and giving this beautiful talk.